Thank you to organizer and everybody. Great pleasure to be here. And I would like to tell about scars and again, this quantum many-body scars. And towards the end of the talk, I will hope to kind of first part of my talk would be more reviewing and motivating why driving is a legit operation. And then I'll try to show that in a flow case setting, the scars are emergent in much bigger quantities sort of and much easier. And try to relate them also to the quantum optimal control problems. And let me just start kind of by the motivation why we should avoid thermalization, right? Thermalization is great and universal, but then if you build some complex quantum simulation apparatus and you don't have any semi-classics, any all-to-all interactions or anything else that kind of protects you, right? You have some bosonic Aubry-André model or some very, very quantum system. Very often you measure some physical quantities here, some configurational correlator, proxy to entanglement, and then interesting dynamics stops at one tunneling time. Right, and then you may ask, why did I do all of that, right? Maybe this is interesting, but maybe I should try to avoid thermalization, right? And then maybe there's going to be more interesting long-time dynamics. And again, today I'll try to start with a review of scars, and then, as I said, move on a bit into driven scar realm, but scars were kind of brought around by this Rydberg atom simulator, and you've seen this Hamiltonian already in a previous few talks, but basically it's an Ising model written in a bit of a special way. Then instead of sigma z here, I will use n, and n is a projector onto spin up or projector onto a Rydberg atom state. And then, let's say in this quantum simulator, you do quench, you prepare special state on a bipartite lattice, you prepare a state where every other, one sublattice is occupied, another sublattice is empty, and you trace its dynamics, and you see that this state revives with a high fidelity. And that's already surprising. Again, I will show or demonstrate that this is highly excited state, very high energy density, so should not revive multiple times. But also something that you see is that there is atypicality, right? This is experimental data that probes occupations on A and B sublattices, right? It's basically quantifying if A is 1, you're in Niel, right? If B is 1, you are in anti-Niel, and you see that for this state there is oscillations which live maybe 1 microsecond, and for this state there is almost nothing, right? So on one hand side we have some states that don't thermalize as fast as we would expect. On the other hand side, it depends on your initial conditions. So now let me try to massage a bit this model in a particular regime of so-called nearest neighbor Rydberg blockade. So I want to use my nearest neighbor interaction between Rydberg atoms as a big scale, right? Assuming it's a dominant scale. And I can do Schrieffer-Wolff transform. And here this PXP model comes, which was used a bit as a, a number of times, but this is actually a derivation of it, right? Which says that under the Schrieffer-Wolff, I'm now prohibiting two upspins next to each other. So this dominant term in my Hamiltonian becomes Rabi oscillations, but constrained by these projectors, right? It says that I am oscillating only if both neighbors are in a ground state, otherwise I'm getting frozen. Then this chemical potential is still there, it's tunable in experiment, we can set it to 0. And then there are going to be some corrections which will pop up in a few slides back, right? But for now I'm ignoring them. And then you can actually visualize, this is very simple Hamiltonian. You can plot its Hilbert space as a vertices, right? Matrix elements are edges connected in these vertices. And now I'm going to show experimental movie, which actually not only shows kind of fidelity revivals, but also shows kind of how state coherently propagates through the body of all product states here and comes back, and so on, right? So this is, and if you wish, if I view ergodicity intuitively, right, that this is big graph. If I increase my system size, number of configurations spreads exponentially. If I spread throughout at once, there should be no reason I will come back. Right? And in that sense, it's also very intuitive notion of, ergodicity breaking that I spread out through the graph, and then by whatever reason, I recohered here and then recohered there and keep doing it. Right? So that's again the PXP model. And once you study Hamiltonian of this, right, you can ask, this dynamics is very strange, anomalous, right? Let's look at the eigenstates, right? Let's check ETH and the eigenstates. For this, we use computer, I don't know, diagonalize big system, maybe have 20,000 dots in each of this plot. So this is 20,000 eigenstates in one symmetry sector. And we see on one hand side, color shows density of dots. So we see that for majority of states, let's say this is bipartite entanglement, right? We see that ETH works for majority of the states, but then we see strange outliers. The same outliers are even more prominent in local observables. This is Z magnetization. Z magnetization is not conserved in this model, only energy is conserved. right? So we see that these outliers are as far as possible from canonical prediction, right? Whereas majority of states concentrate here, right? And if I increase my system size, these fluctuations would become weaker and weaker, and then these 7 states in this particular case are actually the same ones which would be responsible for the Néel dynamics, because when you do overlaps of these eigenstates, this Néel initial product state, you see that these overlaps are large. So these are the dominant states that tell me my dynamics, and you see that energies are approximately equidistant. So that's my revivals, right? The distance between this energy is inverse period of my revivals. So that shows us that the nature kind of is interesting. Nature gives us some cases where on top of ETH obeying eigenstates, there are some strange outliers. So can we understand them? And speaking of eigenstates, our picture that led to some understanding of these states was the following. So we found in 2019, together with Misha's team, we found weak quasi-local, so exponentially decaying deformation of this specific Hamiltonian. And this deformation, it doesn't bring us a symmetry to this Hamiltonian, but it does something quite bizarre. It allows you to have one representation which looks like a SU2 spin within this Hamiltonian, right? So after this deformation, I can split Hamiltonian into raising and lowering operators, and starting from Z2 state, I can create a ladder of states, and it will end in a symmetry partner of Z2. So again, intuitively, in a cartoon way, it means that this representation is like an embedded spin. It's a spin L over 2 that coexists in my Hilbert space with some other states. And, on this spin subspace, Hamiltonian is actually very simple. Hamiltonian is just sigma x. And, one north pole is Néel. This is anti-Néel. Scar oscillations would be just rotating this spin. But then if I start with some other initial state, I am not in this block of my Hilbert space. I am in some other block. How thermal it is actually an open question. But it looks way more thermal, right, than, this one. And these states, right, are specifically these eigenstates of my big spin. So that's, again, one explanation. And again, here there is a certain degree of fine-tuning, right? So far we know one deformation. It also actually still remains a hypothesis. So you need to add some weak terms to a PXP model. And then you get this perfect decoupling. If you have no such terms, then you would have some matrix elements here, right? This would everything becomes more imperfect, right? And then eventually, if you tune far away, right, this probably will smear, right? You have a lot of matrix elements here. I must mention, right, that also, a lot of progress on scarred eigenstates was done by McDowell and Bernevig and others. And there is also another review that reviews kind of these eigenstates in other settings and other models. But we also, in a previous talk, we heard another picture. We heard a picture of trajectories, and that's actually something that I will try to use in the second part of my talk. And for trajectories, we can actually do the most, the simplest thing possible, which again was already proposed by Misha and collaborators, right, by Hannes Bernier and others. Namely, let's do dynamical mean field. But dynamical mean field is bad because naive dynamical mean field will violate our Rydberg blockade, right? If I have, two spins pointing like that, right, there would be some component of upspin here and upspin here, and boom, I violate my Rydberg blockade. So the solution is to project my dynamical mean field onto Rydberg blockaded subspace. Turns out that can be very elegantly performed and gives you matrix product state. And it's a very simple matrix product state. You see it has still one angle, so it's pretty much like my product state. And what I did, I replaced excited weight by a sigma plus Pauli matrix. And it's a magic matrix because it satisfies the equation sigma plus squared equals 0. Right? So this matrix prohibits two Rydbergs next to each other. That's it. I kind of kept pretty much my product state, but now I exactly embedded this Rydberg constraint. And now what Van Wey and Hannes and others did, they did a projection of quantum dynamics onto manifold of such states. So they project Schrödinger equation using so-called time-dependent variational principle. They get very elegant, actually, system of equations, study its phase portrait, and then in its phase portrait, they did find trajectory, unique trajectory, and kind of surprisingly or not surprisingly, this unique trajectory connects Z2 to Z2 prime states. And I must say, right, that there are two notions of Lyapunov exponent here. So this is two-dimensional phase space. It's not generic. I'm not going to discuss Lyapunov exponent within it. But there is way more important Lyapunov exponent here, which I would call quantum leakage. This is gamma. right? Which is a quality of my projection. So I'm doing something pretty brutal. I'm taking big many-body quantum system, projecting into some very small manifold. And if my quality of projection is bad, gamma is big, shown by dark colors. So here this TDVP can be thrown away into trash can, right? In these dark regions, it doesn't work, period. This trajectory turns out to be very lucky, right? This trajectory is in the region where the color is almost white. So you see that it enjoys not only that, there is a trajectory, but also this leakage is low, and that's kind of what protects our system. So later, what we did study more generic phase space with 3-side unit cell, and there indeed you see mixed phase space. So you see more generic situation, and you can find, I suppose you can find infinity of stable and unstable periodic trajectory on this picture, and I just want to illustrate a couple of stable trajectories. So I took low leakage trajectory and high leakage trajectory, and you see that entanglement, and this is now exact quantum dynamics, from a low leakage trajectory does have very, very pronounced oscillations, and then the small linear growth, right? And this linear growth I interpreted as this leakage, right? That my system comes back here in the variational manifold, but then each time my variational principle is a bit imprecise. And that's what gives rise to this growth. And now you see there is a comparable period trajectory here, shown by a diamond, but this is actually high leakage. It's also stable, but actually I don't care about the stability or instability within this manifold, because it's a many-body system. There is a huge Hilbert space out there, and what I care a lot more is how much I leak or I don't leak to it, right? And you see this high leakage trajectory shown by this cover, doesn't have much interesting dynamics. Fidelities, it is damped very fast, right? And entanglement grows very fast. So once again, on the language of trajectories, scars are low leakage trajectories in this variational manifold, right? So I need leakage over a period, right, to be not too strong, and then I'm gonna have revivals. And that's kind of, I think, closes, if you wish, this analogy, right, that we can have, let's say, a billiard, and classically we know there is a chaotic motion. Quantum typical eigenstates look like a collection of plane waves, as we already heard, right? That's a typical eigenstate in a billiard. And then this billiard has a bunch of special trajectories. There would be some marginal trajectory where particles stick around, some time around it. There would be some unstable trajectories. There can be also billiards with mixed phase spaces, right? And then again, I don't want to go into subtleties. There are like a lot of subtleties here. Some states would be called scarred, some would be called regular, but since we are dealing with a many-body system, okay, we are not yet there to make these fine distinctions, but I would call them non-ergodic eigenstates, right? And again, they are analogs of this, or memories of this marginal or some special trajectories, but also you can do revivals, right? You can take a quantum wave packet like this, shoot it, and then you're gonna see many, many revivals. So again, I hope I kind of managed to convince you that this Rydberg system has parallels with kind of both pictures, right? And that's probably legitimate to call it scars. So now, let me come back to experiment, to this kind of very nice simulator. And, it's a very powerful machine. It was really efficiently able to implement the scars on a variety of lattices, chains, square lattice, pretty much number of bipartite lattices, and they show all oscillations, but you see that lifetimes are actually interesting and different. And you can ask, where this lifetime is coming from, right? I showed you already that PXP model needs some deformation, but why is this so damped, right? You can ask. And turns out, right, there is like a no free lunch result here, and nature doesn't want you to have very good scars. Because you take this model and you do Schrieffer-Wolff, and there are two terms beyond that I kind of ignored in the previous slide. And these two terms have different physics. So one of them tells you that if you move Rydberg atoms too close, if you have very good blockade, you have these tails of 1 over r to the 6 interaction. And you're gonna influence nearest neighbor and next nearest neighbor, and you're gonna influence many, many atoms, right? You're gonna interact strongly. So that's again this regime. Another regime, you can move atoms further away. You say, okay, I don't want third nearest neighbor interaction. I'm moving atoms further away, but you're gonna break your Rydberg blockade, right? So you see there is term in the numerator and in the denominator. So there is no free lunch. And the lifetime on a variety of lattices experimentally follows very easy phenomenological formula, which basically tells you that, either this term is killing you, longer range interactions kill you, or poor blockade kills you. And again, you see that V is numerator and denominator here. So there is an optimal sweet spot of V, where these two processes are kind of comparable, right? And namely, you cannot do better. So namely, you can just go to the sweet spot where these two processes are destroying you at an equal manner, and that's it. But then, you know, it turns out that again, there is no free lunch here, but there is free lunch from driving. And starting driving did some magic. Usually you expect from driving that it's not going to make things better, right? It's not going to make things relaxing slower, especially if you're driving at approximately period of your internal system dynamics, right? Because, you know, something oscillates, you start driving the system more, so it's going to oscillate more, right? And going to heat up quicker. What driving actually did to this system is remarkable because you see that in certain regime, driving gives you 5-time increase in this lifetime. So I put a system, I prepare a chain at the sweetest spot where the lifetime is longest possible, and then I start driving it and I get a factor of 5 longer oscillations. Okay, that was interesting. Moreover, right, in experiment or this theoretical simulation, you can see that entanglement also displays non-trivial dynamics, right? You have non-trivial entanglement oscillations which are stable. So you entangle and then disentangle, entangle and disentangle, disentanglement of a single spin. Yet this driving also still maintains memory of scars. So there is a sensitivity to initial states, right? So you see that this driving is not that it did something trivial to your system and everybody is now, you know, broke down your thermalization completely, but you see that, let's say, Niel state is enhanced, and if you look at the zero state, it's not as enhanced, right, by driving. So phenomenology also shows that there is subharmonic locking, so you see that system responds at every other period of your driving, right? And there would be robustness to parameters that I don't have time to show. So actual explanation that was proposed by us together with Nishad and, you know, other people was that this driving realized scar-based zero-temperature discrete time crystal physics, right? You see that number of properties checks, the subharmonic locking, robustness to parameters, and so on. And in some sense, this driving by chemical potential implemented a bit like many-body spin echoes that did stabilize the system for way longer times, right? So this stabilization was explained by this picture. Again, I don't want to go into much more details about this time crystal physics. If you're interested, please look in this reference. But I want to use this as a motivation that driving is actually reasonable, right? So let's think about driven scars. Let's think about scars in the driven systems. And now I would like to stop, you know, for a bit and maybe ask, you know, spend some budget of my question time to ask if there are questions about this first introductory part where I tried to, yeah, yes, please.
So my question is about the, you said leakage is Lyapunov exponent. So we've been thinking about this, and Lyapunov exponent is actually like defined at the infinite time. So it actually, by the ergodic theorem, it is actually capturing like entire phase space information,
yes.
While the quantum leakage is something like it is coming from like really the first order derivatives and really in the vicinity of the manifold. So how, like, is it just an analogy, or is it true that it can go further than an analogy?
I mean, I discussed for a long time with classical chaos people. Generally, many of them don't like Lyapunov exponent. And I think there is a very nice way around it. At least here, with my business, I have a very nice way around it because I do periodic trajectories. There is so-called thing which is called Fouquet multiplier. So you can take a cube at your periodic trajectory, translate it once over a period, and ask how bad this cube got deformed. Right? And that's way nicer than the Lyapunov exponent because it's finite time, and I have the same metric where I started and where I end. And again, you know, classical chaos people would love that a lot more. And I think then this relation would be easier to establish, right? If I would try to establish relation, I would try to establish relation between leakage and Fouquet, kind of, you know, this Fouquet multiplier kind of periodic orbits. Because then I think I have a chance. But you're right, I agree with you that, you know, in a kind of, if I take this infinite time averaging and so on, then this analogy is, you know, I should not be using it, or it's very, very qualitative. So, okay, if there are no more questions, hopefully I'm motivated that it makes sense to drive systems. And now I want to kind of try to switch gears a bit and ask, yeah, again, are these Fouquet scars generic? And also something else that is nice is to have a perfect model. So can we have perfect model with scars? And for that, I actually want to ask a simple question. I give you entangled trajectory. How can you generate dynamics along this trajectory? And hopefully analogy is clear, right? The scars are low leakage periodic trajectory. And now I'm asking, let's start from trajectories, right? Let's forget for now about scars. Let's start with trajectory and ask, what does it take to generate me dynamics along a given trajectory, for example, in MPS manifold, right? And I will be using matrix product states specifically. I want it to be entangled because if it's a product state, I know how to generate it, right? I take magnetic field and rotate my magnetic field and I'm going to generate whatever I want. So how do I do it? And on one hand side, there is story that uses parent Hamiltonians. I can take that every MPS has a parent Hamiltonian. And I can, read classics literature and say that there will be generator of adiabatic transformations, quasi-adiabatic transformations. Calculate this generator. It's not so pleasant, but it's calculable, and then that's going to be my driving. But then we have an MPS, and we do it in an MPS-y way, right? Because, MPS is so good, so powerful, we know the state, we know a lot, right? And that's what I want to discuss, right? I want to discuss how first to do it in an MPS way approximately, variationally, and then I want to discuss how to try to make it exact, also in an MPS friendly way. So to this, let me try to again, introduce this very, very simple idea, which you may view a bit as an inverted variational principle. So in variational principle, in time-dependent variational principle, we have an operator that drives us somewhere, and we project it. I want to invert it. I want to say that you came and told me, let's drive that direction, and here are your two operators. Can we drive there? Right? And that turned out to be a very easy problem, actually easier problem than TDVP. It's still the same minimization. It's a minimization of quadratic form, right? I'm asking, here's where I want to go, and here what I have as my steering wheel, right? What values of these parameters I have to have this minimum? Answer is very simple, right? It's a quadratic function, so you can work out an answer. An answer depends on some pseudometric and some, overlap, and these are both very efficiently computable within MPS, right? So in MPS, I can calculate this is two-body observable, right? And this is overlap of tangent space with a given operator. So it's not a very complicated thing. And then I still also have a measure of control, right? How good I'm driving, and this would be sine squared of this angle. Right? If this angle between my best direction and where I want to go is pi over 2, I better stay where I am, right? I'm not going where I want, I'm leaving my manifold. If this angle is 0, I'm in business, I'm doing perfect driving, right? And we solve this problem, but here, and that's why I think that we need Floquet setting, the idea is that for trajectory, typically this generator is going to be dependent on the trajectory. Right? So I'm solving my problem, I can do very well my driving, but the price I'm going to pay is that my operator will start depending on where I am on the manifold. Right? And, there is no free lunch in the spirit of this talk, and this deviation controls quality. So now I have a Floquet scar recipe. I take entangled trajectory, I take operator set, and I generate you A of S by finding most optimal values of these couplings that bring me on this trajectory. And that's going to be a Floquet system, right, that implements this driving. So can we do it? Well, let's do it for Ising, right? Let's take some MPS, one dimension too small, but generic, it is entangled. Let's take time-dependent transferred field Ising model, and then let's take one extra term that's going to be helping us. And let's throw this for some specific trajectory into this framework, and it just spits out me some time-dependent couplings. So I have a driving protocol. And now I can take the driving protocol and ask, is quantum system following it or no? So I can calculate this leakage, but instead I'm actually comparing my MPS dynamics with exact quantum dynamics. So I'm doing fidelity per site. So if this is 0, it means that my quantum dynamics is perfect. And you see that if I take Ising model with constant couplings, this thing blows up. So you see that I'm not following this trajectory. I'm screwed. Now, if I take Ising model without this term, it's way better. And if I take Ising model with this extra term, it's nearly perfect. And the same happens to entanglement. You see that here is transferred field Ising model thermalization. Entanglement shoots up through the sky, right, at time 5. And you see that taking this framework makes my driving nearly perfect, entanglement growth is gone. So it works. Now, what does it mean in terms of Floquet model? Because we expect actually that Floquet model would thermalize, right? And we expect that ETH also should work there. And even easier, right? Because we got rid of energy conservation. So then everybody should be infinite temperature density, infinite temperature states. And now we can check unitary operator, right? That is one period of this model and check its eigenstates. And then on one hand side, as we expect, a lot of states are volume law entangled. So this is not because, you should be careful with driving. I can do something trivial to you. I can drive system and then undo it. I can do some very, very trivial. I can come up with some trivial protocols that I drive system and then disentangle it. But this proves that this is not the case because majority of states are actually strongly entangled. And yet there are some eigenstates which are actually, very, very low entangled, right? And prediction would be, of course, that if I have perfect dynamics on a trajectory, then this Floquet model would have my matrix product states as an exact eigenstate. And that's actually a pretty strong violation of expectations for thermalizations, that every state has infinite temperature, yet I have one state, which is area law, weakly entangled, but area law state, right? And you see that these states are sort of forming here, but this is not exact. So now maybe one quick glance of yet unpublished results, how to make it exact. And for that, we kind of think about something that I call MPS CRISPR or MPS surgery. So on MPS, you can do the following operation, right? You can try to insert an impurity, which is this time derivative, by a local operator, right? So I need to solve for this problem, and hopefully you see how it's related to my driving, right? That's my left-hand side of a Schrödinger equation. That's my right-hand side of a Schrödinger equation, but just written in a local way. And this operator exists. Is this related to parent Hamiltonians? It can be found. It also has a gauge freedom. It can be deformed by any parent Hamiltonian because, parent Hamiltonian adding here just does nothing to my MPS. And then the only issue is actually in the details is to make this operator Hermitian. And that was, again, we've been suffering for quite some time of how to make operators that solves this Hermitian because, in physics we do Hermitian operators, but turns out that we can construct Hermitian sequence of operators of increasing range, and each of these operators is Hermitian, and we know we have the bound that with range, the quality of our driving or the leakage decreases exponentially. So if you wish, this is a construction that tells you, you bring me a trajectory, I give you quasi-local Floquet model that in regime where range goes to infinity is going to have exactly zero leakage, so it's going to have exact area law MPS. So far, so good. So that's, again, if you wish, now I got less special states. In PXP model, it was Hamiltonian, I had some power. Now here I'm having one MPS state, but still it's a model which behaves very, very atypically. If I prepare it at this CTA, MPS state is going to oscillate and come back. If I prepare it somewhere else, it's just going to thermalize. Okay, so I'm ready actually to conclude. So I started by a brief review of what has happened in PXP model and, discussed two pictures of the scars using this hidden spin and low leakage trajectories. I discussed stabilization by periodic drive. Again, didn't give any theory details, but if you're interested, there is this paper. And then I tried to argue that if we relax and if we view kind of, solve our optimal control problem, we can get Floquet system with Floquet scars for pretty much any entangled trajectory you like. Of course, devil is in the details. It would be interesting to study how ugly or how good is this driving operator, right? Is this driving operator, I saw that Ising model gives you already something reasonable. I showed you, right? But again, the question is how bad or how this operator behaves. And of course, there are many open questions. I would like to thank collaborators. So, Nishat, Doliv, and Alex, who pushed this driven scars and earlier scar business, Marco and Janiv, who is also in the audience, who worked more recently on MPS, more senior collaborators. And with this, I'm ready to take more questions. Thank you.
Okay, thank you, Maksim. So, questions? No? Okay, let me start with one. So, you were discussing, just to check if I understood, you were discussing the impact of this 1/R6 and the fact that
yes.
Rydberg blockade is not enough. So I didn't understand whether by introducing driving, you correct that result and you go back to the PXP, or if actually by doing so, the new Floquet eigenstates are more exact.
Yeah, so actually I don't think that is completely understood. So what we realized is that you can take PXP model, and with driving, revivals improve there still, right? Because PXP model is imperfect, right? And driving helps a lot just for the PXP model. Again, I think it's, you know, the picture is actually very similar to the time crystal kind of picture, where there is, again, natural period doubling and so on. But I think that's an interesting theoretical question, and maybe also for big experimental relevance, what these kind of pulses would be doing to longer range terms, if they're also getting canceled or no. So that's, again, my short answer, I don't know.
Okay, thank you.
So about these like periodic driving, what I'm understanding from here is that you are like steering us in the Hilbert space.
Yes.
Right, like creating like manifolds at each time and projecting on manifolds maybe at each time. Is that true?
No, my setting was more like you have your favorite manifold, you draw a line in it, and you give me the line. And I go on from there. So, you know, if it's, and that's something that we didn't explore at all, right? That now there is this machine, you stick your favorite trajectory into it, and I will spit you out the operator. I don't promise much about the operator. It's going to be Hermitian, right? And if you want exact, right, it's going to be quasi-local. But quasi-local doesn't mean it's a pleasant operator, right, in general. And that's probably like where the devil is. If your trajectory is too entangled, I expect that I will spit you out some crocodile, and you would just run away and say this crocodile is not going to be implementable in the lab. But I think it's an interesting question, which also has to do with expressibility or sort of quantum control, right? That given operator sets, how much states we can access, or given manifolds of states, what basis operators is needed to kind of efficiently navigate in it.
So then, is it necessary, for example, have Floki engineering here, or is it possible to do this with, say, quasi-periodic driving, or maybe just random, any type of like?
Yeah, I would say this is quite different from Floki engineering in this, in the sense that when you use high-frequency expansions, that this is more relies, or this is more coming from adiabatic end, right? That, you know, this whole business of quasi-adiabatic continuity is how to make. If you are adiabatic, you are precise, but you have no time to wait for infinity, right? So you want to be, you know, the trajectories that I showed, you have period order 1. So you want to do something that otherwise takes you infinitely long, efficiently in a finite time. How do you do it? And that was kind of what we have done with MPSs, and now this is, again, this is a SCAR machine.
Hey, I was wondering, would it be possible to use this steering to prepare states with a low energy variance in thermalizing systems?
I mean, very interesting question. And again, I think it's also related, maybe I should discuss, like, for a brief second, relation to the contradiabatic driving that I briefly mentioned. And contradiabatic driving answers pretty much, let's say by Anatoly, answers a very similar question: what is the best operator A? But contradiabatic driving uses very rough metric. Contradiabatic driving uses metric which is a trace over complete Hilbert space. So it's asking, can I connect the full Hilbert space here and Hilbert space there? And then Anatoly himself writes that, look, this operator is going to diverge and it's going to be a physical operator because I'm in a chaotic system. This construction, right, is in the opposite extreme limit. It's the zero temperature, if you wish, right? I'm caring about one single state. What happens to this construction if I increase temperature? It's an interesting open question. Is it going to blow up immediately? Or can I, you know, rotate finite number of states, or exponentially large but measure zero number of states into each other before this operator diverges and stops being nice? That's something I don't know.
Yeah, I had a question. Have you thought at all about the structure of this A of S, like these quasi-local generators, when you have maybe certain assumptions on the Hamiltonian? So, for example, if you have like integrability in an XXZ chain, or if you have some like global SU2 symmetry where, you know, the SU2 symmetry kind of appears miraculously in the PXP, but maybe you can kind of assume SU2 at the beginning and see if there's some, like more constrained structure on these quasi-local operators we've derived.
I mean, I think this A of S, the good set of this A of S would be coinciding with the operators that Polkovnikov calls contradiabatic potential. So the intuition would be that these operators should commute with your Hamiltonian to cancel some of the time dependencies. But our approach gives very different answers compared to Polkovnikov's exactly because of this norm, right? He takes a norm of a full Hilbert space, we optimize. So our approach is just more precise, right? We look at this specific state and optimize for it. Generally, again, I think, I don't have ready answers if it has anything to do with, some of the symmetries, but you could have, if quantum simulator didn't exist, one could rederive PXP model from here, because if you do this construction for PXP model, the miracle is, right, that this A of S is nearly time constant, as not surprisingly, right? So if you would give me your favorite trajectory for PXP, I would rederive your PXP Hamiltonian in some sense, but of course it's cheating, right? Because we know that this trajectory is there, and this kind of start from the trajectory. So.
This might be kind of like a forward-looking question, but it seemed like, if I understand correctly, you're kind of given a particular trajectory, you're able to optimize and kind of prevent the leakage. Kind of connecting this point to more of a quantum control, do you have a sense of like how easy or how hard you can use this to then ask, given a particular initial state and a particular final state, can I find the best and kind of the easiest trajectory?
Yeah, I think that's also, we are looking forward in the same direction, I would say, but we did start to explore it maybe a bit in a sense that, let's say with this, for example, I can take some, I can take my favorite ansatz, right? And for example, I can define good and bad directions, right? Because I did one optimization. I optimized kind of this quantity. I optimized this quantity, right, over C's. But then you can ask, what about second optimization, right? Can I, after finding the best C's, can I optimize now over directions? So can I have some sort of notion of I have experimental basis, and then in my manifold there, it's hard to go, and here it's easy to go, right? And again, I think this is all, and what I like with this, right, is that this is all absolutely trivial from MPS algorithms, right? There is nothing, this is, absolutely trivial compared, let's say, to what was happening in the previous talk, right? And, it basically really solidly puts MPS variables as your semi-classical variables, right? Now I get rid of my complexity. This eta is a control, right? If eta is big, I'm in trouble. I should stop and add more bond dimension if you wish, right? But if eta is small, I'm okay. I trust what I'm doing and just go forward classically.
Other questions? No? Okay, we can thank Maksim again. Since we are at the end of the conference, let's all thank the organizers, so Thomas, Nicolò, Sergei, and also the organizers of the program, which apparently has been a great success also, not only the conference.
Sure. I would like to thank you all, so all the participants, the speakers, all the chairpersons that made, of course, these sessions a great success. And I hope that you enjoyed. Just as a reference, we were about 100 people, so everyone showed up. So we are extremely happy about the success of the event. I look forward to meeting you in either here or somewhere else in the future. So thank you so much, and I pass the microphone to Nicolò.
Okay, good morning, guys, and let's thank Tommaso once again for acting as the main organizer of the conference.